Hello, welcome to 4.5, rational functions and rational inequalities. Okay, rational, think of ratio, think of fraction. Fractional functions. A rational function is a function that can be written in the form f of x equals p of x over q of x, where p of x and q of x are both polynomial functions, and q of x is not 0. Of course, even though q is not allowed to be identically 0, there will often be values of x for which q of x is 0, and these values of fractions undefined. The rational function is undefined. So consequently, the domain of f is a set x is an element of the reals such that q of x is not 0. So I have some graphs on here from the TI-89. f of x equals 1 over x. I'm sure we've seen that before. 1 over x minus 2 means just shifted to the right 2. There's an asymptote through x equals 2. Asymptote through x equals 0. And here's 2x plus 3 over x plus 1. The asymptote is through x equals negative 1. And those lines should be dashed lines here. So a vertical asymptote, the vertical line x equals c is a vertical asymptote of a function f if, or is f of x, sorry, it should be if f of x increases in magnitude without bound as x approaches c. The graph of a rational function cannot intersect a vertical asymptote. So here our vertical asymptote is x equals 1. It's approaching that. Here's another example of being x equals 1. And that should be dash 2. This is x equals 2. It's approaching that. And it'll never cross the asymptote. It'll get infinitely close to it. Horizontal asymptotes. The line, horizontal line y equals c is a horizontal asymptote of the function f of x. If, again, f of x approaches the value of c as x approaches negative infinity or positive infinity. Now, the graph of a rational function may intersect. It happens. It's actually not all that uncommon for it to cross a horizontal asymptote, but it will eventually approach the asymptote from one side only as x increases in magnitude, or decreases. But so here's our horizontal asymptote there. Here's one where it crossed and came back down to approach it. Now, one type of asymptote that you probably haven't heard of is the oblique asymptote, which is kind of cool. Now, this is a non-vertical and non-horizontal line, may be an asymptote of the function of f. The graph of a rational function may intersect an oblique asymptote also. This is also called a slant asymptote, so here's an example of one. Oblique asymptotes. Pretty cool. Now, if it's a line, like in these cases, this is y equals mx plus b. It just follows the equation of a line. Now, asymptote notation. The notation x arrow c with a negative sign means x is approaching c from the left side of it, or what we think is the negative side. Whereas x with an arrow with c at the plus means x is approaching c from the positive side or the right side of it. And then notation x with an arrow with a c is used to describe the behavior that is the same on both sides. It's approaching the same thing on both sides. So in that, if you look at these graphs, f of x approaches negative infinity as x approaches 2 from the left side. So it's going down as you go to the left side. As you're approaching 2 from the right side, it's going to positive infinity. F of x goes to infinity as x approaches 2 from the positive side or the right side. Here, depending on doesn't matter which side you're going from, g of x is going to negative infinity as x goes to 1. So here's our asymptote. Both sides go in the same place. And here, h of x is approaching 2 as x goes to infinity. H of x is going to 2 also as x goes to infinity. So negative infinity to infinity. Equations for vertical asymptotes. The function, rational function f of x equals p of x over q of x has been written in reduced form so that p and q have no common factors. The vertical line x equals c is a vertical asymptote for f if and only if c We're saying x equals c. C is a 0 of the denominator, the polynomial q. In other words, f has a vertical asymptote at the x-intercepts of the denominator. So you find out where your denominator is 0, and that's where you're going to have vertical asymptotes. So in example 1 here, it says find the equations for the vertical asymptote of the rational function. Okay, we can factor the numerator. It's going to be x minus 3 times x plus 1. We can factor the denominator. It's going to be 2x and an x. I think it's 2x plus 1, x minus 3. Okay. Now, so we have x minus 3 times x plus 1 over 2x plus 1 times x minus 3. The x minus 3's divide out. We're left with x plus 1 over 2x plus 1. So this means we have a vertical asymptote at 2x plus 1 equals 0, 2x equals negative 1, or x equals negative 1/2. That's our vertical asymptote. What about the x minus 3? X minus 3 equals 0 means x equals 3. We don't have an asymptote, but we have a hole. There is a hole in the graph. Now, it's not going to show up on the calculator if you graph it because it'll go infinitely close on the right side and the left side, so you're not going to see that. But we emphasize that with a little circle there on the graph. Your horizontal and oblique asymptotes. F of x equals 6x over 5x squared minus 2x plus 3. This is a polynomial in which the denominator has a greater degree than the numerator. Because the denominator is of greater degree, the denominator will grow much more quickly. It'll blow up when the numerator doesn't. So as x goes to infinity, this is getting big and the numerator is not. So you have a horizontal asymptote of y equals 0. So the case is, if your numerator has less degree than the denominator, y equals 0 is your horizontal asymptote. If, however, you have the case that they're the same on top and bottom, these little ones are not going to be that big compared to these others, the 6x squared and the 3x squared, for example, in this case. Which means as x gets big, we're able to look at these two, and what you're going to end up with is just 6 over 3. So in this case, it'd be like y equals 2 is your horizontal asymptote, if they're the same degree on top and bottom. In the third case we have down here, it kind of probably, oh, that says oblique also, okay, so that's okay to have it. 7x cubed plus 2x minus 1 over x squared plus 4x. It's 1 degree higher on top than bottom. This means if you divide it out, you're going to have a linear result. You could drop off the remainder, but when you divide it out through division, you're going to have a line as your asymptote. This is your oblique asymptote. Because it's 1 degree more, it's just a line. It's of degree 1. And this last case, notice it's to the 5th power versus the 3rd power. That's a degree separation of 2. Now you're not going to encounter this in the book. I'm just trying to share that with you because this information is good to have. So you can read about this. But what's really cool about it is its degree 2 difference, it's going to be a parabola, a parabolic asymptote. It's kind of crazy, I know, it sounds crazy. But your asymptote will be parabolic in shape. In fact, if you're ever doing one of these problems, whatever the difference in degree from top to bottom is, assuming the top has the numerator has the greater degree, that's going to be the kind of shape of your asymptote. So if it's 3, it'd be cubic, and so on. Okay, so you're not going to see this, but it's there, it exists. So let's look at some equations for horizontal and oblique asymptotes. Let f of x equal p of x over q of x be a rational function where p is, this should have just been an, nth degree polynomial with leading coefficient a sub n, see I got those in the wrong place, a sub n, and q is the nth degree polynomial with leading coefficient b sub m. If n, the numerator power, is less than m, the denominator power of the horizontal line, y equals 0, is a horizontal asymptote. If n equals n, they're the same power, then y equals a sub n over b sub n. You're comparing the leading coefficients. That's your asymptote. And if n is n plus 1, that is, if your degree on top is 1 more than on bottom, then you'll have an oblique asymptote, and you do your polynomial division to get the equation for that. If it's more than that, you're not going to have a straight line. It's going to be quadratic or cubic. But you're not going to really encounter this one. Okay. Find the equation for the horizontal or oblique asymptote. Well, we have degree 1 more than on the bottom. So we do x plus 3 goes into x squared plus 0x plus 3. That's going to be x, so we have x squared plus 3x, subtracting, negative 3x plus 3, and they're going to multiply both, negative 3 is the next one, so negative 3x minus 9 is 12. We can ignore the remainder. Y equals x minus 3 is the oblique asymptote. The next one, they're the same degree. So y equals the coefficient on top, the leading coefficient on top, over the coefficient down below. Y equals negative 3 is the horizontal asymptote. I'm going to need to scroll up there in a moment, so feel free to pause if you need to. And in C, notice the degree in the denominator is less than the degree in the numerator. Degree of numerator is less than the degree of the denominator. If I said that wrong, I apologize. Degree of denominator. So y equals 0 is the horizontal asymptote. Okay, the steps in graphing. Given a rational function f, factor the denominator in order to determine the domain of f. Factor the numerator as well and cancel any common factors. By setting these factors that can be reduced from the rational expression equal to 0, you will find holes in the graph. You can note these locations by drawing holes. You know, essentially we're really exaggerating that by comparison to how big they really are. But you draw holes in the curve describing the graph at these x locations. Examine the remaining factors in then the denominator to determine the equations for any vertical asymptotes. Compare the degrees of the numerator and denominator to determine if there is a horizontal or oblique asymptote and proceed to find the equations for such. Determine the y-intercept, assuming 0 is in the domain of f. Determine the x-intercepts, if there are any, by setting the numerator of their, this is key. Determine x-intercepts, if there are any, by setting the numerator of the reduced fraction equal to 0. So putting 0 in for x here gives you y-intercepts. Putting the numerator equal to 0 gives you x-intercepts. Determine if there are any symmetry that can be used as an aid. Plot enough points to determine the behavior of f between the x-intercepts and between the vertical asymptotes. Okay, so we have some things to graph here. It says to sketch the following rational functions, making use of your work in the problems from example 2 and additional information. So I am going to refer to the stuff in example 2. about the intercepts and any other points that may be useful. So let me get both these up here. There we go. From example 2a, y equals, what was it? X minus 3 is the oblique asymptote. Also, x plus 3 equals 0, x equals negative 3 is a vertical asymptote. So we have negative 3. Probably should change colors on this, so I'll go blue. Stick it with blue. There's a vertical asymptote. Y equals x minus 3, so we have this. That's what it looks like. Let's get f of 0 is going to be 0 squared plus 3 over 0 plus 3. That's going to be 1. So for the y-intercept, right there, and for the x-intercept, x squared plus 3 equals 0, means x squared equals negative 3, or x equals plus or minus I root 3. So that means there are no real x-intercepts. So that means our curve is going to come down here and go up like that. It's going to come up here. It's going to go, and I'm exaggerating this one. It's going to be further down, just like that one's further up that way. But it tells us which part it's going to be in. Is it going to be down here or up there? And it's down here or up there. We know there are no x-intercepts there, so it can't be up in that area. No x-intercepts there, so it can't be in that area. Okay, for the next one, from example 2, B, we had y equals negative 3 as the y-intercept, or the horizontal asymptote. X minus 2 equals 0, so x equals 2. This is from the denominator, is the vertical asymptote. Now, f of 0 is going to be negative 3 times 0 plus 5 over 0 minus 2. So it's 5 over negative 2. So 0 comma negative 5 halves is our y-intercept. So it's right about there. That tells us something. That tells us we have a curve here and not down below. And for x-intercept, negative 3x plus 5 equals 0. That's the numerator. Negative 3x equals negative 5. So x equals negative 5 over negative 3, which is 5/3. So x-intercept at 1 and 2/3, right about there. It's on the same side over here. There's no x-intercept there. That means we must be drawing down that in that region. So we can draw this down here. Sound effects help, by the way. And then down here. Okay. So we'll make sure the orange shows up on the camera, and it looks like it does. Okay, moving on to the next page. Okay, we have f of x equals x squared plus 5 over x cubed minus 27. From example 2b, we know that y equals 0 is a horizontal asymptote, 2c I should say. X cubed minus 27 equals 0, so that means x cubed equals 27, or x equals 3. That's our vertical asymptote. f of 0 is going to be 5 over negative 27. That's 0, 5, negative 27ths is our y-intercept. No x-intercepts, because x squared plus 5 equals 0, x squared equals negative 5, x equals negative plus or minus I root 5. So curve must be here. Even though there's no y-intercept up there, it's down here, and then there. Okay, you could plot another point over here like 4 to find out where that's going to be, just to verify it. Moving on then to rational inequalities. Inequalities that can be written with a rational function on one side and 0 on the other. There are two ways to solve this, graphically and analytically. And graphically, graph the rational inequality and find the intervals that satisfy the conditions of the inequality, either positive or negative. Analytically, you're going to factor the numerator and denominator, determine the zeros in the numerator and denominator, find test values between Find test values between the zeros by using the test values to determine if the factors, and by extension the entire expression, is going to be positive or negative. The intervals on which the expression is satisfied would be the solution of the rational inequality. Be sure to include the 0 if the inequality is greater than or equal to, or less than or equal to. And the 0 is in the numerator. Okay, so we're going to solve these. First one, we have the guide. So we're going to have 5 over x minus 2 minus 3x over x minus 2 greater than or equal to 0. So 5 minus 3x over x minus 2 greater than or equal to 0. So it's greater than or equal to 0. So y would be equal to negative 3 over 1, which is negative 3, horizontal asymptote. X minus 2 equals 0, x equals 2 is a vertical asymptote. For y-intercepts, we're going to be looking at 5 minus 3 times 0 over 0 minus 2, 5 over negative 2. So 0 comma 5 over negative 2, that's going to be an intercept. A y-intercept right there. And then what else do we need to know? X-intercept. That's going to be where 5 minus 3x equals 0. So 5 equals 3x. That's where x equals 5/3. Down here then, because we have no intercepts there. So we're looking where this is going to be greater than or equal to 0, and that's just going to be in this region right here. So it's going to be, solution is going to be from 5/3 to 2. That's it. Solution. Now we could look at this in terms of the chart. We have zeros at 5/3 and at 2. So if we pick something like 0, pick something like, oh boy, 11/6, pick something like 3. For 0, 5 minus 0, that's positive. This is negative. The result is negative. Put 11/6 in there. That's negative. This is still negative. This is positive. Put 3 in there. Negative, positive, negative. So between 5/3 and 2 is our solution. That verifies it with the chart. Got one more to do. Let's do this, knock it out of the park. Now, in this next one, bring everything to one side. You have x minus 1 over x squared minus x minus 6 less than or equal to 0. This is x minus 1 over x minus 3 times x plus 2 less than or equal to 0. So right off, I mean, we can look at the chart, but I don't want to graph this one. So the thing is, nothing cancels out. But our horizontal asymptote is going to be y equals 0. We'll have vertical asymptotes where x minus 3 is 0, means x equals 3. X plus 2 is 0, which means x equals negative 2. For y-intercept, that's going to be, put 0 in here. 0 minus 1 over 0 squared minus 0 minus 6, so 1/6. For x-intercepts, that's where x minus 1 is 0, where x equals 1. Okay, so I think we can graph this now. We're looking for a place this is less than or equal to 0. So we have this, crossing there. And typically, unless it's squared, if it goes down on one side, it's coming from above over there. If it goes up on one side, it comes from below, like that. Okay, now we're looking for places this is less than or equal to 0. So that's going to be satisfied by this region. So solution is going to be negative infinity to negative 2 union from this point, which is at 1, 2, 3, and then that's it. Now in a chart setting, let me just do a chart real quick here. I think it's pretty clear to see we have the zeros of 1, 3, and negative 2. So negative 2, 1, and 3. Do it over here more. So we have x minus 1, x minus 3, x plus 2. I'll go negative 3, I'll go 0, 2, and 4 for those test values. So we put negative 3 in here, that's negative. Put negative 3 in there, that's negative, that's negative, that's going to be negative. That's why that region works. Put 0 in there, we're going to have negative, negative, positive. That's positive. That's this part here we're seeing for up to that. Put 2 in there, we're going to see positive, negative, positive. That's going to give us negative overall. That's this part, and why that works. Put 4 in there. You're going to have positive, 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 positive. They're all positive. That's that part. So our solutions were right here and right here. Okay. I know it's a pretty involved section. Thank you for your time. Send me your questions. Thank you.